So we haven't done any work yet in the course yet. We're going to do work today. We're going to do work, right? Work. Get it? Okay, I got more jokes too. So work is defined as a force applied over a distance, okay? And it's quantified as force times distance. So in metric units, it's Newton meters, right? Force is in newtons, distance is in meters. So that's not minus, that's multiplication. That's multiplication. Newton meters. And Newton meters are joules. One Newton meter is 1 joule. And this is the units for work. In English units, that'll be foot pounds, right? So force in English units is pounds, distance is in feet. So foot pounds is our English unit for work. So this is Midvale School for the Gifted. So if work is force applied over a distance, then our bright student here is exerting how much work? He's pushing really hard on that door. How much work is he exerting? A lot of work? No, zero work, right? Zero work because work is force applied over a distance. It's force created to move something, right? So even an immense force applied over distance, zero yields 0 joules of work. Okay, and then also in the spirit of what we're doing so far this semester, so if I've got, let's see, what can I push here? Here we go. So what about, am I doing work on this chair? Yeah, so it takes a force for me to move it, and then I'm moving over distance. And so then the amount of work that I've exerted is increasing as I go, right? So it's accumulating, right? Work is accumulating. And so at any certain point, there's a total amount of work that I've accomplished in applying that force over the distance. Okay? So this idea of accomplished work up to a certain point fits right into our spirit here of accumulation of a quantity, right? How much work has accumulated, in this case, over a distance, right? How much work has accumulated over a distance? Okay, so it's going to be more complicated than just taking a value of force and multiplying it by a distance. Why? Because force can vary as you go, right? So as you're exerting or accomplishing this work, the force may be varying. Okay? And then the distance might not be nice and simple straight line. So this is what complicates the issue. It's not just the force is 8, the distance is 5, 8 times 5 is 40, right? So it becomes complicated when force varies and distance can vary. All right, so let's talk about the pushy ant. So the ant pushes a seed along the path shown, and the ant pushes with a constant force of 0.03 newtons. How much work will the ant have accomplished at each distance along the path? Right, at each distance along the path. So what is if we want to figure out the accomplished work or the accumulated amount of work, what are we going to need? Rate of change of work, right? So that's what this is showing here. So the name of the game is if we can get the rate of change of work, then just like any other quantity, all these other quantities we've been working with, it's the same thing. We'll be able to quickly write down what the work accumulation function is, right? Okay, so how does rate of change fit into dW? So dW, so what would I write here that relates to the rate of change of work? dW equals what? Force times distance, okay. All right, so force times So what is distance? So here, so we're going to have, so notice that my independent variable is x. So we're going to think about this. In the coordinate plane, right? So we're going to have to model this path using coordinates, right? So we'll have x and y coordinates. And so then what is distance? If a little bit of work, if work is force times distance, a little bit of work is a little bit of force times a little bit of distance. What is the distance? A couple people are saying arc length. Is it dx or is it arc length? It's going to be arc length, right? So now we're interested in arc length. But then eventually, so then we're going to need it eventually in terms of x, right? So we want that function of work as a function of x. But when we think about a little bit of work that the ant does, it's going to be according to arc length. So this would be force times, what should I write here? D arc length? S, right? Little s. Right? And so then our force will be most naturally would be given as a function of how far we are along the path, right? So force is a function of how far we've gone times a little bit of going along, right? A little bit of distance, and that'll be our little bit of work. And then our goal is to get the rate of change with respect to x. Yeah.
So the independent variable for the force function is the length of the path.
That's how it would naturally be given, right? So if we actually was measuring or modeling the force required, that would be the force in the direction along the path. But then we know how to relate these two. So that's we can take care of that because that's what we've been doing all along, getting arc length as a function of x, right? So that's no problem. But naturally, if you're thinking about modeling this in the real world, the force function that you would have would be as a function of where you're going, how far you've gone, or where you're going, not your x coordinates. But we will kind of do a transformation from arc length to x. And we already have all those tools. Okay, so here is the if we now, like I said, we're going to put it the xy coordinates, and we've got the path is this function. So this is the path function, path of the ant. And the force is constant at 0.03. So what will dW be? We said it will be the force as a function of arc length ds. But in this case, what is the force? Yeah, it's just constant, right? So 0.03, that's no problem. So all we have left to do is we have ds, but our goal is what a rate function in terms of x. So how do I get that? I've got ds. A little bit of work is according to moving along the path a little bit. How do I get that in terms of dx? So you just apply what we've learned. What is ds? Yeah.
Square root of 1 plus f of x squared.
Square root of 1 plus?
The derivative of f of x squared.
Is that it? dx. Remember that? We've done that, right? We've done that. That's what a little bit of arc length is. We use the Pythagorean theorem to kind of make that transformation from ds has to do with the hypotenuse of the little triangles, right? And so this transformation then gives it to us in terms of the horizontal variable, right? So therefore, what is the rate of change of work as a function of x? Looking at that, if dw is 0.03 times that square root times dx, then now we know what the rate of change of work is with respect to x. What's the rate of change of work with respect to x? Yeah.
Would it be the integral of 0 to x, and then that, or dw?
I think you're thinking about the accumulation of work. I'm asking about the rate of change of work. So what would the rate of change of work be? This form of an equation should be very familiar. We've been hammering it all semester. dw equals something dx, right? Therefore, the rate is the something, right? This is just like dy equals mdx, right? That's what we have. Now our y is work. The y is the quantity work. So we have dw, or like dy, equals something times dx. Therefore, that something is the rate, 0.03 times the square root of 1 plus 5 of x squared. So here's the big takeaway. The rate of change of work is what quantity? What quantity is the rate of change of work? Force, right? It's force. And this is just transforming it from arc length into the x variable. That's all this square root does. It's like unitless, right? This is like unitless, and it just is a transformation from the direction of the curve to making the independent variable x. So it's just transforming that force into the horizontal variable that we need. So this is force, right? The rate of change of work is force. That's what this is. It's the 0.03, just transformed from arc length variable to x variable. So that's a big takeaway here. The rate of change of work is force. Okay, any questions on this first example? We'll put it in. Let's see. So this is kind of the easier example. So we'll not. Let's do it. Okay, so we'll put this into GC and see what we get. Any questions on the setup? All right, so here we go. First, we'll do the force function. Okay, and then we have what is our arc length function? What's our arc length function? A comma x. So we can just put the rate in. So the rate work to x is times what? Square root. Do derivative. This we can do. This is x. This is fine. Okay. And then we're ready to write the work function. So what do I want here? What am I going to put in? R sub W of t. Need a different variable than x. Okay. What do you think? Have I done this correctly? What's that? Thank you. Yes, that's right. If I'm gonna tell it to do the derivative of my path, it needs to know what f is. Very good. And what was that? Do I have it incorrectly? Okay, so what do we expect to see? So if I'm going to graph this, I'm going to graph work as a function of x. What do you think, can you predict what the graph will be like? So I'm going to do y equals, right? To graph it, you do y equals w of 0, comma x. And that from, looks like we'll do 0 to 3. So when I graph it, what will we see? Can you make a sketch of that graph? What do you think it'll be like? Decreasing, increasing, wavy. Where does it start?
Axis means in the original function, like for the original function of x means like how much is changing the x direction, right? Y.
What is that?
Is that what it's saying? In the original function? You get what I'm saying, though, right? Like if you were to look at a bird's eye view of like the ant is going.
So where will it start? So at x equals 0, what will the y value be? Negative, 0, positive. What will the y-intercept be? So at x equals 0, how much work has the ant accomplished? 0. So it better start at the origin. And then what's it going to do from there? Decrease? Work will decrease? Negative work? So will the work decrease at the start, or will it ever decrease? No, work is going to accumulate positive because the work is calculated, right? It's in the direction that the ant is pushing, right? Always, right? Now that's going to be a function of x, but it's always going to be, the work is going to be a forward push, right? The ant is pushing along this path in the forward direction, so it's always accumulating positive work. Right? That means the function will always be increasing, right? Increasing. So yes, it'll always be positive, but that's because it'll always be increasing. So, and it's a little bit wavy because for some values of x, the ant does a lot more work. So say around, as x changes from 0.2 to 0.3, for that change in x, the ant does a lot more work because it has a lot more distance to cover than say from 0.3 to 0.4. Its increase in work is going to be less because it's not covering as much ground for that change in x. But it's always going to go up. It's always going to be positive, accumulating positively. So that's the work profile. So if I click on this point right here, 2, 0.17, what's the meaning of that point? 2, 0.17 on this graph. means what? Tell the person next to you. What does the point 2 comma 0.17 mean in this context?
Like, is that like the path it takes? Or is that like the rate?
Okay, what do we think? Yeah.
At 2, or a distance of 2, is it producing 1.7 or 0.17 newtons?
Okay, so when the ant's gone a distance of 2,
Yeah.
when the ant's gone a distance of 2, it's the force that's producing a force of 0.17 at that moment. What do we think? Is this at the moment quantity or an accumulation quantity? Okay, it's accumulation, first of all. Accumulation of what? Work, right? So this is all the accomplished work of the ant, right? This is in Newton meters. So what's the 2 mean then? When what is 2? Distance the ant has gone? When the arc length is 2? Great, what is it?
It's when the ant has gone 2 meters from 2 meters left to right from wherever it started.
Right, so remember this is the x coordinate. We did this function, this work accumulation function as a function of x. So it's gone further or less, or not as far as 2 meters, the actual distance the ant has traveled? A lot farther than 2, because it's doing this crazy, this up and down thing. So as it's doing all that work going this crazy up and down thing, the amount of accomplished work when it gets to an x coordinate of 2 is the 0.17, is the accomplished work so far, or the accumulated work. Right? So its distance, by this point, its distance, the distance traveled by the ant is a lot more than 2 meters, because it's making a curvy path, right? So it's gone a lot farther than 2 meters, but this function is measuring work as a function of x. So it's right when the ant is right here, about right there, it's accomplished 0.17 Newton meters of work that far, so far. Does it make sense?
One
Yeah.
unit's just X.
So it would have to be meters, right? So this graph would have to be in meters, and so then this is the same as our work graph. It's going to have the same units as this. It's going to be meters and then Newton meters on the other graph, this graph. So on this graph, it's the same x coordinate as in the x coordinate of the path graph. It's the x. Does that make sense?
Not yet. but I'll watch the video again.
Why not? That's not too bad. So on this graph right here, this is meters going this way, and this is meters going up. So this is the x-coordinate of the position of the ant and the y-coordinate of the position of the ant. We built the work function as a function of the x-coordinate of the ant. So it's going to have the same exact axes when we graph the work function. This axis will be exactly the same. Is that better?
So just to be perfectly clear, on the first,
I wasn't perfectly clear?
oh no.
Sorry, go
No,
ahead.
I just, or, just kind of
Sorry,
reiterate,
I'm just kidding.
on the first graph, that's just like, that was the path. On
That's
bird's eye view,
That's
right?
the path. Bird's eye view, right? This is meters horizontal and meters vertical. So looking down, and the ant is, yes, right. Or it could be crawling on the wall, right? So that could be, but yes, it's a view. These is meters and meters, and this is the path of the ant actually walking. This one now is graphing for that same x coordinate on that path graph. The work you get this way. Yeah, Nick.
So when we explain the point
Uh-huh.
2.07 meters, yeah, we would say when the ant has reached an x coordinate of 2.
Uh huh. Yeah, when the ant has or traveled horizontally 2 meters or reached an x coordinate of 2, yep, the accumulated work is 0.17 Newton meters. Okay, any other questions? All right, so let's, so that's pretty simple so far. So it gets a little more complicated when, that's the wrong thing, this one. So what about if the force changes? So far we had the force was constant. So same path, but now the force is a function of s. 0.03 times s plus 1. So meaning as the ant keeps walking, the force required is increasing. Maybe what is the ant pushing? It's pushing a seed. Maybe the seed is gathering dust or gathering some kind of, residue, or whatever. So the seed is getting heavier, and then the ant has to push harder. So as distance increases, the force increases. So how are we going to handle this? Now we have F as a function of S. Okay? We have the same path of the ant, but now force is a function of S. So I'm going to take attendance. So there's a little bit of a challenge to this. It's not super hard, but you have to think about this and figure out what you're going to do to create the rate function. That's really the whole name of the game. Once you get that rate function, we're home free, right? So this takes some thinking, takes a little bit extra work here. So see what you can come up with, work together. So either you're working on it or you're making progress or you're getting some help. Okay, so I'm going to take attendance, see how this goes.
I think it's just like the same.
No, it's a little bit harder.
Okay.
It's a little bit harder. You're not going to just be able to write it down. Okay, let's see how we did. Brian, did you make some progress on this? Tell me. So you're saying what is S? You're saying what you need to figure out what S is? Okay, so let's do that here. I know what F is. So you're saying you need to know what S is? What's that? What did you decide that it was? Oh, so it's the same. So it's this. Is that what you did? Kenny likes it? Right. Good. So we need what we need is capital F of X. And so in order to do that, you're saying that arc length is the same as the path, f of x. Let's see what we think. Anthony, what do you think? You agree with that? Okay? Yeah?
I don't agree. It wouldn't have to be the arc length function, so it would have to be a square root of 1 plus f derivative, or f derivative squared dx.
Okay, so this is not f, but instead it's
Arc length.
arc length. And arc length is?
Square root of 1 plus f derivative x squared dx.
Is that arc length?
Or,
That's the rate of change of arc length.
oh,
Is that what S is? So Nick?
It's the integral from AX of the rate of change.
So he wants the arc length function, the integral, the accumulation function. What do you think? So what do we need? Yeah, if we're going to write the force as a function of x and we have it as a function of s, then we need this. We need arc length as a function of x. What is arc length as a function of s? Is it f? Is it the square root? Or is it an integral function? It's the arc length function. It's the arc length function. So that s as a function of x is integral from a to x of square root of 1 plus f prime squared times dt. And so that would have been with t, right? So this is s as a function of x. So we can take that and put it in, oh, sorry, oops, right here. That's S, so we can put it in there because then we need f of S, and that's what S is. And when we do that, so this is like a composite function, right? F of S, where S is a function of X, will give us f of X. And then the rate of change of work will be, what will the rate of change of work be? So what would I write for the rate of change of work? Okay, so what you're writing is you're saying f of S of, and we want 0, right? Times. So it's still f with this transformation, right? The square root gives us the transformation from arc length to x. But now our force function is different, right? Our force function is not just a constant anymore. We have to get that force function as a function of x, the horizontal coordinate. And that means, and we're given it as a function of s, distance along the arc. So then we have to replace that s with the arc length function. And then our work is going to be what? Once we have the rate, then we're home free, right? Once we get the rate right, we've got it. So let's go to GC. Let's put this in GC. Any questions? Does that make sense? So when we get to the work function is going to be what kind of function? Integral, right? It's accumulation of work at this rate, right? Accumulation of little bits of work at this rate. And that rate function is based on what? An accumulation of little bits of arc length. So we're going to have a kind of nested accumulation function, kind of like we had when we did the distance traveled last time, right? The distance traveled it had this nested accumulation of with velocity as the rate, and then that was accumulation with acceleration as the rate. So questions before we go to GC. Does this setup make sense? Yeah?
Capitalized W, A of X, that is total, accumulated work.
Right. Accumulated work starting at an x coordinate of A out to X. Yep, accumulated work. And this is the rate of change of work. This is capital W2. All right, so let's put it in here. Let's change this up here. So let's turn off the graph. Let's call this one work 1. Okay, so we'll call this work sub 1 for the constant force, and that's the one we graphed first. That should still work. Okay, that still works. And so now we're gonna build a work 2 function, which is with a variable force, right? Variable force. So let's see here. I'll call that. Uh-oh, didn't like that. Can I do double subscript? I don't know. Let's try. See if it works. Oh, it worked. Good. Okay, so I got my rate function for work 1. I got my work 1 function, and I graphed the work 1 function. Little f is the same for both. So now we're going to change it up here. And that's F1. Still works. Great. So I got everything subscripted with 1 for our constant force scenario. Now we got the variable force. So we're going to start with the capital F. Capital F is, so capital F sub 2 of S is what? What's the force function now? 0.03 times s plus 1. And then we wanted to get, we need to define what our arc length function is now. So s a comma x equals integral from a to x of square root 1 plus this thing. So I'm going to copy and paste. Go a lot faster. But that needs to be t and t and t. Now we're ready to write the rate function for rate 2. So our rate, control W, control 2. What did we say? It's going to be f of s starting at 0 until x.
Why do you have to start at 0?
Because now we need to tell it what, so this is only a function of x. It's not a and x. So we're gonna, if I put a comma x and I didn't define a, it's gonna do a default and it's gonna start it at 1. So here, this function's only of x, I gotta tell it everything else. Yep. So it's gonna be this whole same thing again, right? But with x's. All right, feel free to ask anytime in here. Well, we got the time while I'm typing in. Did I make a mistake? Did I lose you? So this is the rate function. It's going to be our force, which is given as a function of s, but we need to get it as a function of x, which means the arc length function, which is arc length as a function of x. So we got this composite function in there. And so that gives us force as a function of the horizontal coordinate. And then the rate of change of work. We need the transformation from going along the curve to x coordinates. So both the force and our independent variable, everything's in terms of x. So now we're ready to do the work 2 function. Which I think is just like this, but with work 2. So I'm going to copy and paste and change it up. Is it right? Okay, we'll do that one red. Okay, and so I'm going to graph it, and what will I see now? So I want you to predict what the graph will be like. Say I haven't graphed it yet, so maybe compared to this one. What will it be like? So while I type it in, you think about it and talk to the person next to you. What will the graph be like compared to this one?
It's gonna take a lot. It's gonna make it a lot more complicated. Or you're gonna have to see a lot more work because as long as there's work, the increase in I think so. Exponential. Oh, okay. Yeah, that makes sense. Yeah, that makes sense. It has like a big
Eric?
For the coordinate, we have to be f sub 2 s 0x.
Yes, thank you very much. So he's noticing that I defined f sub 2. I need the f sub 2 right here. Thank you. Did I do any other mistakes like that? I think I'm good. All right, prediction. So will it be always increasing like the first one? Yeah, but it'll still always be increasing, right? We're still increasing in work because we're traveling along the path. We keep pushing. So we're gonna, and how will it compare to the first one?
Increase a lot faster.
Increase a lot faster.
Maybe exponential.
So what about at the beginning? How's it going to compare at the beginning for low values of x? Similar, right? Because when they haven't gone anywhere, what's the force? Same as before, right? When s is 0, it's 0.03. So for low values of s, the force is only going to be a little bit bigger than the constant force. But it's for higher values of s where you're going to see a bigger difference. Okay, and then there's something else we're going to observe here. Any other predictions about what's going to happen when I hit graph? He says it's going to take a long time. Why? Right. So in the spirit of accumulating bit by bit, it's going to take even the technology. It's going to take a while because it's having to do it twice within itself, right? So it's having to accumulate these little changes in arc length with s, and for every one of those, for every one of the changes in the work, according to the force, it has to do the whole arc length function every time. So this is what we talked about last time, and it's the idea of open form, right? Open form does not conveniently calculate results, and so when you get open form nested within itself, it even takes the technology a long time to do it. See that? So this is reiterating that open form, these integral functions, they're great at showing us the meaning behind it, right? Accumulating or summing up lots of little bits of change. That the meaning is right there. But in terms of calculations and results, it even takes technology a long time if you have this case of two accumulation functions having to both be evaluated simultaneously.